Yeah, so as I was saying, yeah, so luckily this is a lecture that I could give in my sleep, so I will. Okay, so we're not going to go through everything that I wanted to do on the syllabus for this class. So if anybody actually wants to, if anybody wants me to, I'm happy to give extra lectures after the quarter has finished on some of the stuff that there was like a week of things that I thought I would get through, which in the end we went more slowly, and I never did those things. If anybody wants me to give those lectures and promises to show up and bring 10 other people with them, then I will give those lectures. Otherwise, today's the last lecture. Okay, so and then next week is the final exam, and I will send you in email information about that. Okay, well, and so on. Okay, so let's get right to it then. So what we did last time was we worked out the simple mean field theory of the Ising model, the nearest neighbor Ising model, and we calculated the emergent critical behavior, the idea that below a critical temperature, the magnetization of the system just goes from nothing but above TC to something non-zero below TC. And we worked out the mechanism for that in mean field theory. And then what we did was we looked at a response function of the system, which is the susceptibility, which tells you how the magnetization varies with external magnetic field. And we calculated its critical behavior. And we saw that that actually diverges to infinity at the critical temperature. And I gave you a physical interpretation of that. And then we ended the lecture by comparing these two calculations that we did in class with the exact results in 2 dimensions due to Onsager, and then numerical and renormalization group results in higher dimensions. And what we saw is on the left-hand side, we saw that beta, the exponent that tells you how the magnetization varies as you go just below the critical temperature, it grows with a square root power law. And we saw that the susceptibility diverges with a 1 over T minus TC power law. And then in the second column, D equals 2, are the exact results from Onsager's solution. And you can see that they're quite different from the mean field theory ones that we just calculated. And then if you look in the third column in 3 dimensions, you see that the renormalization group and computer simulation results are getting closer to the mean field theory results. And then in the right-hand column, you can see 5 dimensions. And in 5 dimensions, you can see the mean field theory is exact. And so that was where we ended. And I made the comment that if you're in higher dimensions, a spin has more neighbors. And so if it's got more neighbors, then each spin is feeling the fields from more and more neighboring spins. And so it's going to look more and more like sort of, quote, central limit theorem. And it's going to look more and more like the central limit theorem, then the mean field theory, an average plus small fluctuations will work correspondingly better. And so that's your intuition for why this happens. But your intuition won't tell you why it is that when you get to 4 dimensions, or above 4 dimensions, then mean field theory is exact. It's not like, well, it gradually gets better and better until you get to an infinite number of dimensions where it works. That would be what you would expect if it was simply the central limit theorem. It's definitely not the central limit theorem, but it's related to it. And in fact, there is literally a discontinuity in the exponents, at least a gradient discontinuity in how it depends on dimension. And that is exploited in renormalization group theory, which is the topic of a course that I usually teach in the spring. Okay, so I'm going to talk today about scaling and data collapse. I'm going to show you that, and then we'll talk about the importance of the thermodynamic limit. And then if I get time, I will talk a little bit about fluctuations and dissipation and talk about what's called the fluctuation dissipation theorem, and maybe introduce you, if I have a chance, to stochastic differential equations. And if I was going to give you another 2 lectures, I would have 2 more lectures on stochastic differential equations. Okay, so the next point I want to make, the one where we ended, was the following: the critical exponents that we have found What do they depend on? So you might have said, well, our Hamiltonian for the Ising model looks like this. So H is the external field, J is the exchange interaction between the spins. And so what you would have said is, well, our model, our Hamiltonian, has two parameters, H and J. And so that would suggest to you, if you were just thinking in a linear way, you'd say, well, if I'm going to have that M magnetization goes as Tc minus T over Tc to some power beta, and the susceptibility diverges as something like 1 over T minus Tc to the gamma, something like that, whether I'm above or below Tc. You would say, well, naively then, we would say that well, maybe gamma and beta are functions of H and J. That would be a very sensible expectation. You've got a theory, it has two parameters. You calculate predictions from that theory. You would expect those predictions would be parameter dependent. And so you would expect that this behavior would then have H and J dependent. And the big surprise is that gamma and beta are just numbers. Independent of H and J. And so what that means is that we call this one type of universality. And why do I say one type of universality? Well, let's just talk about universality. So universality in this context means that the predictions are the same for all magnetic materials. So if you're looking at iron, you're looking at nickel, whatever it may be, you may say, well, these are different magnets. They have different properties, different chemical structure, different different atoms and so on, different spins. You would think that these things would be different, but they're not. So they don't depend on the parameters in the theory. So that's the big surprise, and that's called universality. It's the same for all magnetic materials. Okay, so that's the first thing, and our mean field theory explains that. Now, there's another thing that comes out of this. I say it's one type of universality, so you might say, okay, what are other types? So here is another example. So let's suppose I take the liquid gas coexistence curve. Okay, so you're going to say, wait, what are you talking about here? We're talking about magnets here, not liquids and gases. Okay, but hear me out. Okay, so let's remind ourselves what the liquid gas coexistence curve was. So if you remember, what we did was we drew a picture that looked something like this. So here is pressure, here is the volume, and then I drew the isotherms, and above Tc, the isotherms were sort of roughly like the ideal gas, and then below Tc, they went sort of like this. And if I drew them at different temperatures, they would be doing something like this. Something like that. And if I were to join up these points here. So these curves are all temperatures which are less than Tc, and as the further I go down, the further below Tc they are. So this one here is the one at Tc, this is the Pc, and this is the critical volume. And this curve over here is an example of what's happening inside this region is you're getting a two-phase coexistence. And so then you might say, well, if I look at the difference between this volume and this one, so these are the two volumes. This will be V liquid, and this will be V gas. Sorry, wrong way around. So this is the volume per particle. This phase here is the gas phase, and this phase here is liquid phase. This is liquid gas coexistence. And if I were to look at this difference here, that is a difference in volume per particle between the gas and the liquid phase. So I could also plot this picture in the following way. I can plot it like this. Density, which is proportional to 1 over the volume. And up here, I'm now going to put temperature. And then if I draw this coexistence curve, it will look something like this. And this will be the critical temperature. This will be the critical density. And then if I'm below the critical temperature, say at this temperature here, I go across like this, I can read off over here and over here. This is the density in the high density phase. So this would be liquid. This would be the density in the low density phase. So that would be gas. And that would be the densities of two coexisting phases, liquid and gas. And if I were to ask you the following question, what is the shape of this curve of rho L minus rho G? So that is a quantity, we'll call that delta rho. So delta rho is a function of T. And you might ask, what is that shape? And that shape, the answer is that delta rho of T goes like Tc minus T to the power beta. And that power beta is 0.325, blah, blah, blah. The same beta that I had for the magnet. Well, this is the beta for the liquid gas coexistence. So that is quite amazing. So it says, I don't even have to have this theory, this Ising model theory, be just describing a magnet. Even if I describe something like a liquid and a gas transition, which is as different as you can possibly get from a magnetic transition, the critical behavior of it is exactly the same. So in fact, the critical behavior of the liquid gas transition is identical to the Ising ferromagnet. It's not just like, oh, it's approximately the same. It actually is exactly the same thing. And so this is another form of universality. So then you might say, well, okay, that's incredible. So then is it the same number for every phase transition? And the answer is no, it's not. Excuse me. Thank you. Is it the same critical behavior for all phase transitions? So the answer is definitely not. No. So then you say, okay, fine, this is getting kind of annoying. Okay, next question is, what determines the values of these critical exponents? And what do we know it's not? So it's not the actual system. And it's definitely not the parameters in the Hamiltonian. And so what it turns out is that the answer is that it is actually two things: symmetry and spatial dimension. Those are the two things that matter. And these things, these combination of variables, symmetry and dimension, that constitutes what's called a universality class. So this was quite a sensational discovery when it was made in the 1960s and 1970s. So then you might say, well, okay, suppose I believe that. Why a liquid? What is the symmetry? What is the same symmetry shared by fluids and magnets? And that's a very natural question. So anybody here want to guess an answer? If you know the answer, then don't say. But anybody here want to guess an answer? If you don't already know it. Okay, you either all know it, the answer, so you're not answering, or um, or you've never seen this before and you think that I've gone completely crazy and you have no idea. It's the latter one. You're all nodding. Yeah. Okay, I thought so. Okay, let me explain to you what it is. Here it is. So I'm going to show you why a fluid is really a magnet, at least a certain type of magnet. Okay, so here on the right is a box, and inside the box are particles bouncing around. So I've just taken a picture of them, and maybe they're in this configuration like that, let's say. And on the left, I've got a magnet, and I'm going to draw this configuration. See if I can do it right. And then all the others I'm going to draw as down. Okay. So basically, you can now see what the dictionary is. So on the right-hand side, I have either, so this means there is a particle, an atom or something. And on the left-hand side, I have a spin that is up. And if I have on the left-hand side a spin that is down, then that means that there is no particle, a hole or gas. So if you give me a configuration of a magnet, I can draw a configuration of a gas where the gas are particles that live on an underlying lattice. So underlying this is the idea that there is a lattice here, and these particles can hop around on a lattice. And so we call this thing on the right-hand side, we call this a lattice gas. And then this thing on the right, on the left-hand side is just the Ising spinor half model. And so you can see that I can draw a correspondence, and in fact, you can then show that these things are really, I can take the partition function for one and map it into the partition function of the other, and that's done in chapter 2 of my book. So the symmetry that they both have is in disguise. This one has a sort of up-down symmetry. And I'll show you what that is. I take the Hamiltonian without an external magnetic field. So there is the Hamiltonian. And now let's suppose I were to say, let's send all the spins to negative values for all I. So if I were to take every spin, if it's up, I make it point down. If it's down, I point it up. So this is a global symmetry operation. And you can see that if I take the, let's call this transformation T, which I'm going to call time reversal symmetry. So then you can see that if I take the Hamiltonian for all the spins, and then I take the time reversed configuration of all the spins and compute the Hamiltonian, you can see that it doesn't change. Because if I change the first spin I to minus, I get a minus sign. If I change the second spin to minus, I get another minus sign. Two minuses make a plus. And so the Hamiltonian is invariant under this operation. So this has a global symmetry operation. And you can show, and I'm not going to spend time in the class to do it, that if I write down the corresponding Hamiltonian for the lattice gas, then it also has this this same symmetry. Okay, and so that's in my book. Okay, so that is the other form of universality, and what it means is that the study of phase transitions and critical phenomena is a study of minimal models that exemplify one particular universality class and may describe a whole host of phenomena. The Ising model is famous not because everybody liked Lenz and Ising's paper in 1925 or Ising's PhD thesis, or even cared that much about ferromagnets. It's famous because you can take the Ising model and then make it into a model of anything you like, from social science to physics to material science to alloys to even understanding the yield of pistachio trees in California. Okay, and I'm not joking about that. Okay, so the Ising model is famous because you can take any system you like and say, I'm going to make a model of whatever it is that sounds implausibly complicated, and you can make some cooked up physics theory of it that will look like the Ising model and claim you've solved it. And physicists, of course, have had 30 or 40 years of practice doing that kind of thing and annoying all the other scientists in other disciplines by the way they do this. But this is what one can do. Okay, you have a question?
Yeah. in the lattice gas, though, like why would the constraint not affect things? Because you have to have conservation of particles, right? But you don't have to have conservation of like total up or down spins. That doesn't matter at all.
It does. It does. So it's a very good question. If you so I don't want to take time to answer that. Okay. In my book, I go through that in chapter 2. But come to my class next year if you want to know the answer to that. Okay. Basically, what you have to do is you have to look at the lattice gas in the grand canonical distribution. So the mapping is actually between the grand canonical distribution and the canonical distribution for the magnet. And the thing that ends up looking like the pressure is something to do with the chemical potential. And it's actually a combination of chemical potential and temperature. So it's an excellent question. And it's not a trivial one. But you can see that there is this configurational mapping, and then you can think of the two body interactions between particles as being like the spin interactions in magnets, and that's how you do it. All right. Okay, so that's the second type of universality. Now the next thing I want to so I didn't tell you, so I told you about symmetry group, I mentioned about dimensionality, and I didn't explain why all these things are true, and there's a whole course literally on that. Here's another thing that is I want to just mention as something fantastic. If we go back here to the summary from last time. So if you look on the left-hand panel, you can see the critical exponents, beta and gamma, in 3 dimensions. And you can see as I've written them down as 0.325 dot, 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 and the other one is 1.24 dot, 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 and so on, okay? And you may say, well, you know, why are they like that? Why aren't they like a half or a third or 17th or something like that? Well, the answer is the value of those critical exponents is in 2D. In 2D, you can prove they are rational fractions. And the proof of that goes back to work that was done by Belivin, Polyakov, and Zamolodchikov in the early 1980s, and Friedan and Schenker just slightly later. And what they did was they showed that all two-dimensional critical phenomena can be explained by a conformal field theory, and conformal invariance is particularly important in 2 dimensions. And so from that, you can do a lot of very sophisticated quantum field theory and then calculate all of the critical exponents for 2-dimensional critical systems. And that was actually one of the birthplaces for what came to be known as string theory. Okay, so in 2D they're rational fractions, but generally speaking, in 3D and higher, they're not, at least as far as is known in general. And then you might say, well, okay, how do you compute these exponents? Okay, so how to compute them? And the answer is, you might say, well, you know, maybe we can just use dimensional analysis to compute things. I mean, after all, you know how to use dimensional analysis in physics. You've had it drummed into you in physics and engineering. You use dimensional analysis, and you can prove, you can prove Kepler's laws. You can even work out what is the speed of a rowing boat as a function of the number of rowers in it. It goes like n to the 1/9 power. Okay, you can do things like that by dimensional analysis. So you might say, okay, that's amazing, fantastic. So why don't we just compute all these critical exponents by dimensional analysis? And the answer is you can do that. And if you do that, the results that you get, you can do that, are wrong. But not only are they wrong, they're wrong in an interesting way. Actually, what they are is they actually are equal to mean field theory. The mean field theory results actually come from dimensional analysis. So if the results disagree with mean field theory, then you would say, well, wait a minute. If you disagree with mean field theory, and mean field theory is the same as dimensional analysis, are you telling me that dimensional analysis doesn't work at a phase transition, at a critical point? That seems to be the conclusion. So people started to wonder, how the heck can this work? How can there be critical exponents that are not the ones we get from mean field theory? So the answer is yes. It seems as if dimensional analysis breaks down at the critical point, or in the vicinity of the critical point. And if you come to my class on phase transitions and renormalization group, or what here is called emergence and phase transitions. Okay. In the first lecture, I will explain to you how the class is about a list of things that are absolutely impossible to occur, of which this is just one of them. So this problem became so important that when it was solved, the person who solved it, there were other people who solved it, but this person who received the Nobel Prize for solving it, they solved it because they received it not just because they solved this problem, which was like, this problem we don't even have an idea of how it's possible to have a solution to this problem. It turned out that solving the problem completely turned upside down our view of what it is you're doing when you're doing physics. It turned upside down our picture of reality. And so if you want to read about that, you can read a recent review article that I wrote for a book called 50 Years of the Renormalization Group. It's on my website, and you can just read that and learn from that. So the bottom line is, it does seem as if the dimensional analysis breaks down the critical point. Other things happen that are very counterintuitive, and I'm not going to spoil the fun. So if you go to my other class, my graduate class in phase transitions and the normalization group, the whole class is spent on resolving this problem. It's a very, very deep and very interesting problem. Okay, so then you might say, okay, that's great. Thanks so much for telling me that I've got to take another class. But let me just show you one thing though. Let me show you how we could get these exponents, the ones that I just showed that we did last time using mean field theory. Let me show you how you can have derived those exponents yourself in 10 seconds using something morally equivalent to dimensional analysis. So the next thing I want to talk about is what in my other more advanced class I call a 10-second theory. For critical exponents. Okay, and I call it the 10-second theory, but it's really, you spend 5 seconds of that theory just applauding and admiring what you did in the previous 5 seconds. Okay, so let me give you an example of this. Okay, so the thing that we did last time was I showed you, whoops, daisy. Well, never mind. I showed you that here is temperature, here is the magnetization, and I showed you that the behavior of this is like this. It's 0 up to here, and then it comes up like this and approaches 1. And the question that we want to know the answer to is, at this point TC, what near this point, as m goes to TC from below, it goes like that. And the question we want to understand is, what is the exponent beta? Okay, so that's the question. And we derived it by mean field theory, and it was, interesting. I explained it to you and all that. But let's see how you would do this if you had 10 seconds and you had to solve this, or else something terrible would happen to you. So the 10-second theory of this is you say, okay, let's flip the curve. So flip the curve. It's going to take me longer to write it down for you than it would be to actually do it. So now I have, my picture looks like this. So on this axis I have m, and this axis I have t, and the curve that I drew is this one, and now we're going to ask, instead of m as a function of t, we're going to ask t as a function of m. Okay, so let's now make a theory for t as a function of m. Well, we know that this Ising model on the left-hand side has this time reversal symmetry. So this symmetry here is called time reversal symmetry. It's not a very good name because there's no time in equilibrium stat mech, but never mind, it's called time reversal symmetry. So because we know it's time reversal symmetry, then what we know is on the other side of here, this curve comes down like this, and this goes to negative values of m, like that. So therefore, I know that if I want to write down the theory for t of m, it's equal to a constant, which is tc, and then some other coefficient, and then it's got to be symmetrical. If it has to be symmetrical, it must be an even function. If I'm going to do a Taylor expansion of an even function, then the first term that comes in there has to be m squared, if it's a Taylor expansion. And then there can be higher order terms, but it has to go like that. And then if I take this and rearrange, then I get m goes like tc minus t to the power 1/2, and therefore beta is equal to 1/2. So that's the 10-second theory. And you could do the same thing for susceptibility and so on and so forth. So this is just to show you that, the fact that this result, I just derived it for you in my 10-second theory, and it's a really clever little 10-second theory, right? Okay, it's not that bad, okay, but it's wrong. And where did we go wrong? What mistake could we possibly have made in a theory which is one line of algebra? Okay, it's very, very difficult to pin it down, and eventually we now understand it, and I'm not going to tell you what the answer is. Not in this course. Come to my next course and I'll tell you at the end, after you've sat through 20 lectures on the normalization group, which you'll want to do. Everybody stays. Okay, so that's universality. Okay. I showed you critical exponents for thermodynamics. So, for example, the magnetization, the isothermal susceptibility. You can do one for the heat capacity. The heat capacity also diverges. It goes as T minus Tc to a power which we call alpha, alpha, beta, gamma, delta. There's another one. There's another one. So this is heat capacity. This one you've seen before. Chi goes as T minus Tc to minus gamma. This one, m, goes as Tc minus T to the power beta. There's another one, which is, do you remember in when we looked at the magnets, the power magnet, we derived Curie's law. You remember Curie's law? That tells you let's see what it tells you how m is proportional to the applied external field. It tells you how it's proportional to that. So there's another one which says m goes like M would normally go like H. That would be linear response theory. So as if I take a magnet, apply an external magnetic field, then the magnetization that the external field induces will be proportional to how strong the external field is. If the field is weak, and then you double it, you would expect the magnetization it induces to be doubled. That would be the normal thing. That breaks down at the critical point. So in fact, it breaks down, and I'm going to now show you how it breaks down. Okay, so this thing here is the breakdown of linear response theory. So it's not just dimensional analysis. But linear response theory also breaks down. And so that's what I want to talk about now in a minute is other forms of other scaling laws. But what I want to mention is there's also scaling laws, also critical exponents for correlation functions. So we talked about the 2-point correlation function. So correlation functions also have scaling laws, and those are understood as well, but we're not going to do them in this class. Okay, so now I want to talk about a different type of data collapse, a different type of scaling data collapse. I think this is the most profound form of critical phenomena, and it's often overlooked. And when people talk about phase transitions, they always want to be able to compute power laws and things like this. I don't give a damn about a power law because I don't believe people can really measure them properly. So what I think is much more important is data collapse. So let me explain that to you. So here's what we're going to do. So the question that we're going to ask is, what is the form of the equation of state near the critical point? So let's go ahead and calculate that. And we kind of already did the work, because in last lecture, I derived for you, when we derived the susceptibility, I derived for you the equation of state. So remember, here was the equation of state on the left-hand panel in green in the middle of the page. So we wrote out the exact mean field theory equation of state. Hyperbolic tangent of h over kt is some big mess on the right-hand side in terms of m. And then we simplified it near the critical point and showed that it had a particular power series expansion. And then we computed the critical exponents from that. And actually, by differentiating the equation of state, we derived the equation for the susceptibility. So we might say, well, is there a simplified form for the equation of state? And the answer is yes. So let's go and derive that. So what I'm going to do is we're going to define a new variable, t, which is T minus Tc over Tc. So that's going to be how I define T. And I'm going to call this thing the reduced temperature. And before I'd had a variable which I'd called tau, which was T over T, and it was Tc over T. And I used that one because it was simpler in those terms to work out the equation of state. But now it's going to be easier to use this quantity. And so in terms of my tau variable, this thing is 1 over tau minus 1. Okay, so why do we like this parameter? Well, you would say this is a good parameter. This should be useful because it is small in the critical region. And what do I mean by the critical region? i.e., critical phenomena occur as t tends to 0, from above or below, that just says that T tends to TC from above or below. So that variable is a small parameter. And why do physicists like small parameters? It's useful because if it is small, then it says that you can use perturbation theory. Okay, so the physicists like small parameters, then we can do perturbation theory. You've done it in quantum mechanics. You've seen a little bit about it in statistical mechanics. So you'd say that's how we solve the problem. So you might think that, but it turns out that it doesn't work. Okay, perturbation theory doesn't work. And again, I'm not going to tell you why. You have to come to another class and I'll explain to you why it doesn't work. Why this is a small parameter on paper, but actually when you write it down properly, you discover that what is actually a small parameter is in fact actually an infinitely large parameter. And so that's why you can't use perturbation theory. So all the physics that we thought we knew how to do goes out the window with phase transitions. So it doesn't work. And if you want to know why, you can look in chapter 7 of my book. Okay, so we're not going to do any of that. Of course, we're going to do something which only requires a few lines of algebra. So now let's write down the equation of state. For the equation of state, I'm going to define a variable which I'll call little h, which is h over kbt. And if you go back to the formula that I wrote down last time, which had m and then m cubed and then some taus and tau squared and tau cubes, and so you write that all down, it looks like this. It looks like m into 1 minus 1 over 1 plus t plus m cubed times 1 over 1 plus t times 1 minus 1 over 1 plus t squared plus dot, 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 a whole bunch of things like that, which are sort of fairly messy. And if you then, do some little algebra and rearrange this, what you find is that you get h is equal to mt plus, I think I've left out a factor of 3. So I'm going to put the 3 in, but don't, I don't know where the 3 goes. I'm pretty sure I've made a mistake here. I don't remember where the 3 goes. I think it's. I don't know. There's a factor here that's missing. I'm just not going to put it in. I'll correct it later. Okay, so this is the the equation of states. So there might be a numerical factor. Okay, so then so that's the equation of state, and then there's correction terms which look like t times m cubed and so on and so forth. So then if I look at that, I can say, well, let's suppose h is equal to 0, and that means that mt plus m cubed is equal to 0, and so that means that either m is equal to 0 or it goes like minus t to the 1/2, which is the square root law that we already had before. So this equation of state, you can very easily see the scaling of the magnetization. So that's that. But there's another thing that you might notice. So let's look into this. So this is at the critical point. So now we're going to look at small h and small t, like so. And so I'm going to write this equation of state in the following form. h is equal to t to the 3/2 times m over t to the 1/2 plus m cubed over t to the 3/2. Okay, so if you look at that, if you multiply it out, look at the cubic term, the t to the 3/2 cancel. If you look at the term proportional to m, the t to the 3/2 divided by t to the half just gives you t. So I haven't done anything. I've just done a very clever multiplication, and so then I can say that, oh well, then this is of the form t to the beta delta times some function of m over t to the beta, like so. And here, my phi as a function of its argument, phi of x, is x plus x cubed. And beta is the one that we already calculated, 1/2, and delta, whatever that is equal to 3. Okay, so that's a true statement, but seems very useless. But here's what you can do with it. So suppose I were to then say, all right, I'm going to measure um, m as a function of h and t. So that says it's a function of two variables. Right? Actually, it's not. It's really just a function of one variable. So let's see why that is true. So I have this form. H is equal to t to the power beta delta times phi of m over t to the beta delta. So that's what over beta. So now you say, okay, fine. So I'm going to take measurements. I'm going to measure h for different m and different t. And if I were to do that, then what I would get would be something like this. And what I'm going to draw is just a sketch. It's not meant to be very realistic. So I'm drawing h as a function of m, and I'm just going to draw a couple of curves here, which are completely fanciful. So they're different curves like that. So, and these would be for different temperatures. Okay, and the and this would be the highest temperature, and this would be the lowest. So that's what you would get. And now then, suppose you said, okay, that's great, but how about we now take a look at our mean field theory? What does it predict? Well, it says if you take m over t to the power beta, and you have the right value for beta, and I have h, and I plot it over t, or absolute value of t if you want, to the power beta delta, and I have the right power of beta delta, then actually what I have is all the data collapses onto some curve that looks like this. And if I'm below TC, actually above TC, then my data might look something like that. So this is T less than TC, sorry, this is T greater than TC. Like so. And the data fall onto a universal curve both above and below TC. So these are data taken at different values of magnetization and temperature, and then when plotted in this way, so this is called scaled data or data collapse. And mean field theory predicts data collapse. And it predicts the scaling function. And that scaling function is what I call phi of x over here. It's this thing over here. That's the scaled data collapse. That's the curve that if I were to draw it above and below TC goes right through those data points like that. And I didn't bring the picture. I should have brought it with me. But I'll post it in Teams, show you the actual data for this. The data is amazing. Okay, it just works. And you might say, well, what does the scaling function depend on? Well, the scaling function is universal because this is the function in this particular case, x plus x cubed. Yeah, 5x is x plus x cubed. So it doesn't depend on h, doesn't depend on j, doesn't depend on t. It's just a universal number. And so mean field theory predicts this thing. All right. So it predicts one more thing. Okay. So then suppose that we have t equals tc. If we have t equals tc, then that means that little t is equal to 0. And so our equation of state is h is equal to mt plus m cubed. And now we've set t equal to 0. So this term now has gone away. And this then says that h is equal to m to the power delta. And this delta is equal to 3. And that is the delta that comes in over here into the universal scaling function. So that's the physical meaning of it. And this h going as m cubed, this is the breakdown of linear response theory at the transition. Mhm. Yep, because m goes like h to the power 1/3 rather than m going as proportional to h as it would do if it was Curies law. And so that's what we mean by the breakdown. And so this is the the result. So let's summarize then, because I've now finished what I want to tell you. So the summary. So mean field theory, which is self-consistent, predicts the following. One, it predicts the existence of a phase transition. It predicts the critical temperature. So if you go back a million pages, so we derived that the critical temperature, Tc is equal to 2d, the spatial dimension, times J over Boltzmann's constant. So it predicts that. It predicts critical exponents. It predicts scaling functions. It predicts universality in its various forms. And what else? And it predicts data collapse. Not bad for a 10-second theory, which is really a 5-second theory. And the theory I presented last lecture was, I don't know, 20 minutes or whatever it took me to explain it to you. So it's not bad. Okay. All of these predictions, all of these things here are directionally correct. When I say directionally correct, It means they're not quite correct. Okay, it means the exponent values are wrong. So the critical exponent, it gets the wrong value. It gets that correct. It gets this correct, but wrong function. So the scaling function is wrong. The existence of a phase transition, it usually is right for that, but there are exceptions. It gets the critical temperature, that's not correct either. So it gets the universality class correct most of the time. It predicts the phenomenon of data collapse, but then the wrong actual function. So it is correct in its direction. It tells you this is what's going to happen, and it's amazing. And then you might start to look for it, and then you find that it doesn't work, and you need RG to do this properly. So you need RG and field theory, etc., to improve it. And that's a whole other course. Okay, so I do want to make one last comment. So in the homework, so in homework 5, I asked you to derive, using dimensional analysis, the equation of state for an interacting gas. Right, I did that. That's in the homework, right? Right. So in the homework, you derived that P over PC is some function of V over VC and T over TC, something like that. Okay, you're asked to do that for an interacting many-body system. And you did it not by doing cluster expansions and all of that stuff, but by dimensional analysis. And why you could use dimensional analysis was that you had a bunch of materials, all of which had a pair potential, which had the following form. It had some energy scale times some function of R, Ri minus Rj over some sigma. And so the class of materials have the same f of x, the same function, but different epsilon and different sigma. Epsilon is the binding energy, sigma was the hardcore radius, and that looks like a data collapse. So you might say, that's interesting. So you might say, is this data collapse? Bless you. Is this data collapse? And the answer is no, it's not. Okay. Why isn't it the data collapse that I've been talking about in this lecture? Okay. When the data collapse I'm talking about in this lecture, when does it occur? Phase transitions, occurs near the phase transition. This data collapse, the one I just showed you on the left-hand panel, when does that occur? Somebody else. Here's the way.
Equilibrium.
All of this is equilibrium. Everything we talked about is equilibrium. In transition is equilibrium. If you wait on it. Phase transition can go out of equilibrium. That's a whole other story. It's called critical strain. But everything we've talked about is equilibrium. In the homework, what is the limitation on the results that you're asked to derive? And
They all have the same functional form for the energy.
they have the same functional form for the energy, so they have to be the same class of materials. Like you can't compare argon and sodium, but if you compare argon with krypton and xenon and neon, they will all work because they all are closed shell orbitals and things like this. Okay? So they have to have the same function for the pair potential, just as you said. But what is the restriction in terms of where you are in the phase diagram? That's what I'm asking. So what we talked about today is being all asymptotically close to TC. We did all sorts of approximations, even in mean field theory, to be arbitrarily close to the critical point. What is the approximation we're making in the other one? Good. Say it a bit louder.
We don't have them.
We don't have one. There's no approximation. We use dimensional analysis. Okay, we took the functional form. I ask you, take the partition function, write it down, do some simple high school manipulations. Bingo, you find that the partition functions are the same. And therefore the equations, the states are the same, but when rescaled by the value of the critical point. There is no approximation. So these occurs throughout the phase diagram. And this is a consequence of the class of materials. They're all noble gases, for example. Okay, so this thing, so this one here is an asymptotically close to TC result. This occurs, this is an exact result given the class of materials. So they're not the same thing, but they are often confused as being the same thing. Okay, but they're not. Okay. Okay, we have 7 minutes left. Do I want to start another topic? Are your brains full? Yes. Okay. I will start very quickly at another topic, but I'm going to do this in a very quick way. I can. I want to just answer one mystery for you. Okay, here's a mystery. It's a mystery. Here's a mystery. The mystery is this. Why is equilibrium possible? Okay, so you might say, well, it's the subject matter of this class, but there's something very strange about it. So think about it like this. Think about it like this. Let's suppose that I have a pendulum, and I make the pendulum so that it is, I'm going to draw it in a sort of exaggerated way, but here is my pendulum with some mass like that and some rod of length L. Okay, now we know that this pendulum is immersed in air. So there's air molecules floating around. And those air molecules float around, and every now and then an air molecule will collide with this pendulum and maybe move it to the right, and then maybe a little bit later, another molecule will come in, bounce off like that. And so what I would expect is that as I look at this pendulum, if I look at some later time, it might be like this. So the pendulum is being bombarded by particles, constantly hitting it and moving it around. And so what we would expect is that the pendulum is going to fluctuate. Right? So the pendulum is sitting there like this, and an air molecule comes in, bangs on the pendulum goes off like that, and another one comes in, bangs the pendulum, it goes like that, and so on and so forth. So the question is, why doesn't the pendulum absorb the momentum from all these collisions and start swinging like crazy? Right? So if you go to the park and there's some parent there with a little kid in the swing, and the parent is sitting there going like this, and the swing goes like this, and then do it again, and eventually the kid gets swinging higher and higher and higher. Why isn't that happening to the pendulum? Yep.
Getting pushed from each direction equally, or like want to play it like that?
Pushed in all directions equally. Okay, that's a good answer. Yep.
It's random. So the average is out.
Random. So average it out. Any other answers?
Also, if it would start moving, there'd be drag
Mm-hmm.
from all the particles we're saying that collide.
Mm-hmm. Right. Okay. Okay. One more, and then we'll move on.
Air molecules are tiny.
Air molecules are tiny. Okay. Well, okay. We know that. Okay. So these all of these things are kind of correct, well, particularly the last one, they are correct, but let's try to compute what we're going to see using statistical mechanics. So let's do a calculation. Okay, and we can do a calculation like this. Suppose I write out the potential energy of the pendulum. Okay, so we know what that is. So we know that the potential energy, I'll just write it down for you, is mgl times 1 minus cosine theta. Okay, that's just the potential energy. So now I can, so let's say that theta is small. So this is approximately, I mean, in practice, you know the pendulum just sort of hang like this, so it's not doing this. So let's just say that let's do a Taylor expansion. So then this is equal to mgl times theta squared over 2. And so then the question is, what is the probability of finding the pendulum at the angle theta? Well, we know what the potential energy is. We know that kinetic energy doesn't matter since we're doing classical stat mech. So I know that the probability distribution for theta is going to be proportional to the Boltzmann factor, which is going to be e to the minus v of theta over kbt. And that is going to go like e to the minus mgl theta squared over 2 kbt. So we know that that's the probability distribution for theta. Okay, so that's the first thing we know. If I know that, then I know what the moments are. The moment of theta, the first moment, the mean is going to be 0 because it's a quadratic function. If I were to calculate the expectation value of theta, well, I know that, sorry, the expectation value of v of theta, that is the term in the Hamiltonian. That term in the Hamiltonian, I can calculate what this is using which theorem in equilibrium statistical mechanics? The equipartition theorem. So the equipartition theorem says that if I have a term in the potential which is quadratic in a degree of freedom, and there it is, theta squared, we know that the expectation value of the Hamiltonian, or that term in the Hamiltonian, is what? Must be what? 1/2 kT. That's what the equipartition theorem says. And you can just do the integral yourself, but that's just proving the equipartition theorem. So therefore what we know then is that the expectation value of theta squared is equal to kbt over mgl. So we know that in fact there is some root mean square deviation from the average, from the vertical position, but and that distribution is a Gaussian distribution to very high order, and that distribution has a second moment which depends on the temperature. So what is happening here is this is exactly what you collectively said, that the thing is that this is non-zero, and it depends on temperature. And if it depends on temperature, then that means it's an equilibrium thermal statistical property. And the reason for this is roughly what you said, but it's something slightly different. Okay, so the thing that causes the fluctuations Write it down a little better. This is important. Fluctuations are caused by the impacts from the air molecules. The drag is caused by the collisions with the air molecules. In order to have an equilibrium, it must be that the fluctuations equal the drag. And when you have drag, you have dissipation. So fluctuations equals dissipation. Okay, as something moves through a medium, like I just run my fingers over this blackboard, which I'm not going to do, there'll be a noise, and that will make a sound that you will hear, and there'll be energy lost from my fingers, okay? So that it causes dissipation. So what you've seen is that equilibrium is tied up with the fluctuations equaling the dissipation. And that's why you can have equilibrium. And this is a theorem, it's called the fluctuation dissipation theorem. And it is something that is very interesting, and I'll tell you why. So if you look at the formula for the pendulum, theta squared is kBt over mgl, and that was for, this was for air, right? Pendulum was in air, okay? Suppose I now put the pendulum in treacle or honey. Okay. So you guys don't know what treacle is, but you know what honey is. Okay. Forget about treacle. It's best that you don't know about it. It's healthy. It's healthier not to know about it. Okay. So this is in air. What is it going to be in honey? Why? Why? No, go ahead. Go with what you're about to say.
I mean, it's on two sides, the more likely it is to get. This part of this article is on it on two sides, so you get more force on one side, you could also get more force on the other side. Like you just,
So you're saying, am I trying to translate? You're saying that there's more dissipation in the honey?
the more, because there's more drag, there's also, it's also more likely for the particle to.
Yes. Yes, there's more drag because the honey is more viscous, but there's more particles that are then hitting the particle, hitting the pendulum and causing it to fluctuate. So they have the same cause and they cancel out. And here's how you know that the answer is true, because the difference between air and honey is what physical quantity, apart from their taste? Viscosity. Where is the viscosity in this formula? It's not there. Okay, so it's equal to the same. That's exactly what you were saying, that the dissipation has gone up. But then in the higher density gas, sorry, in the lower density gas, wait, the dissipation has gone up because it's more viscous. Okay, and then there. But also the fluctuations have gone up because there's more dense particles hitting the pendulum, very roughly speaking. And so they bounce in equilibrium. So this fluctuation dissipation theorem is a requirement for equilibrium. So I want to finish. So let me take the questions. And I got one more thing I want to say. So then you might say, well, can you tell the difference between air and honey? So let me do a simulation of it. Here's my computer simulation. Okay, the simulation uses my arm. Here's a pendulum swinging in air. It swings roughly like this. It's swimming at its natural frequency, and then whoops, an air molecule hit it, so it bounces, and it swings, and another air molecule hit it, and so it swings like that. So that's what it does in air. What is it? Does anybody like to do a dance interpretation of what a pendulum would do in honey? Anyone? I did the air one. Anybody want to do the honey one? No? No takers? You're no fun. Okay, I'll do it. Okay, it's going to look like this. It's moving really slowly, and then there's a little jiggle, sort of like this. Okay, so reasonable, fit your intuition. Okay, so the difference is the air one is underdamped simple harmonic motion. And the honey one is overdamped simple harmonic motion. And so if I took the, so what I would do is I would take the power spectrum. So let's take the power spectrum. So what I do is I take my theta as a function of time. So here's my time. Here's my theta. I take its Fourier transform. And then I take the power spectrum. And then take the average over this probability distribution. And then I plot that as a function of frequency. So let's draw it for the pendulum. Okay, so the pendulum has a natural frequency of omega naught, which is square root of g of rel or something like that. So what's happening if it was just oscillating at the frequency omega naught, its natural frequency, I took the power spectrum of it, I took the Fourier transform and then took the absolute value squared, what I would get is I would get a delta function at omega equals naught, at omega equals omega naught. Okay, because it's a sine omega naught t, then I take the Fourier transform of that, work it out, and you'll see you'll just get a delta function at omega naught. So if there was no air, it was just swinging, it would be like that. But it's got a little bit of dissipation because every now and then it does bump into a molecule, and the molecule causes a bit of drag, and also then basically kicks the pendulum and keeps it going. So that's what it would be if it was ideal, and in reality it would look sort of something, something like that. And so that would be the power spectrum you would see for pendulum. If on the other hand, you did it for the honey, well, you know, this jiggling thing, if you look very carefully at my jiggling arm, you might see that it has a natural frequency of omega naught. So that's that little peak just here, which is now definitely not a delta function, definitely not going to infinity. It's just some little bleep. And then there's broadband frequencies at all different frequencies, because this thing is fluctuating in this sort of jiggity way. So this power spectrum tells you, so what P of W tells you, P of omega equals the energy in the range omega to omega plus d omega, something like that. So it tells you in the air case, all of the energy is located in the natural frequency omega naught, and in the pendulum in honey, the energy is distributed over all the possible frequencies. And so anyway, so this is a property of equilibrium, and I'm not in the notes. There's a whole chapter on the connections to this. So this is a critical property, an important property of equilibrium. But most importantly, it talks about now for the first time we are discussing time itself. In other words, we're now starting to get infinitesimally away from thermal equilibrium. And that's why there isn't a course of statistical mechanics 2 in this department, which there should be, but maybe there will be one day when I've had a chance to mess with the entire course catalog. But there is a class on non-equilibrium statistical mechanics. And if I were teaching that class, which I probably will have to do at some point, that is where you would make the bridge between the two things. Okay, so I have more or less covered pretty much at some level of superficiality most of the topics, pretty much all the topics that I wanted to cover. I wish you had a semester so that I could teach these things in as much detail as in my lecture notes, but there's always another time. So I hope you've enjoyed the class. I hope you've learned something from it. I hope you've been taught not just from the lectures, but from the homework as well, and that I hope that this class will be useful in your research. So thanks very much. And before you go, what?
Treacle, what is
Treacle. What is treacle? Oh, it's easy. Treacle is like honey, but it doesn't taste as good. So course evaluation. So how many people here have done the